Okay, so it's already 6:12 and nobody has joined yet. So I'll just begin the class on my own. Today's class will be mostly theory, so lots of notes. I'll share all these notes, of course, as I've been doing in the previous two classes. Uh, yeah, so that's how I'll proceed today. So yeah, the way I'll go about today's class is that I'll first write down all the theory and then I'll explain. Mostly the notes will be self-explanatory, but still, since it's just theory, it's better to get all the information in one place. Nobody is joining, I think. Okay. Huh. So today first we'll look at what happens inside an AS. What are the components inside AS? Okay, so I'll just first write down all the notes and then we will go point by point, okay? So just bear with me. So the first important component is what is known as a hollow cathode lamp. Okay, so like this, I will tell what are all the important components. So number one, number two, number three. We will go step by step from start to finish, and I'll write a short note for each of them. Okay, so the first important component is what is known as a hollow cathode lamp. It emits specific light, and for each metal that we want to detect, it will have its own separate lamp. For instance, if I want to detect the arsenic level in groundwater, I will have a special lamp for arsenic. Likewise for lead, zinc, aluminum, whatever. Okay. So each lamp is designed for one metal, and it emits a few sharp lines near the absorption line of that element. Okay. For instance, arsenic means it will emit a few sharp lines near the absorption line of arsenic. So what is absorption line? I'll come to it next now. Okay. So absorption line is a specific wavelength of light that an atom absorbs out of a light beam. Okay, so when you emit light, it will contain many wavelengths, right? So when it passes through a material, that material has some cloud of free atoms. Those atoms will only absorb the light that matches their internal energy levels. Okay, so what is internal energy level? Like we talked about earlier, right? Like the energy level because of the electrons that the atom which the electrons which occupy the outer shell of an atom. Okay, so each of the electrons will have particular energy level, like steps in a ladder. We saw all that in the previous classes. And electrons can only jump from one level to another level when you give a certain quantized amount of energy. Okay, so I give you the example of stairs. Okay, so all discrete values, it's not continuous like a slope. So electrons only jump to from one level to another level when they absorb the right amount of energy. Okay, so that's what we mean over here. So as the light containing many wavelengths passes through this cloud of free atoms, uh, whichever matches the internal energy of that particular atom, that light will be absorbed. Okay, uh, so this unique light fingerprint is what we call as the absorption line. Okay, if you want, I can write it in terms of words. Light will contain many wavelengths, right? Wavelengths will represent by lambda. Okay, so that ladder analogy, what I'm telling is that atoms have got fixed energy levels, like the steps of a ladder, and electrons can only jump to higher steps by absorbing the right amount of energy, not more, not less, leaving a dark gap in the line in the spectrum at that exact wavelength. So this unique fingerprint is what we call as an absorption line. For instance, zinc, right? It absorbs light at wavelength of 213.9 nanometer. Okay, so the zinc lamp that we will be using for detection of zinc, it has to emit at this particular wavelength so that the free atoms in the zinc can absorb it. So that's a unique fingerprint. Okay, so one question you may ask is that why is it called cathode lamp? See, we give the example. It's hollow cathode lamp. It's because the lamp contains a cathode made of the element that you want to analyze. For instance, if you want to analyze arsenic, it's made of, it contains a cathode made of arsenic. Okay. Uh, like you must be familiar with anode, right? They're just electrodes. Okay. And they, through which, uh, like the cathode is where reduction happens, that is gain of electrons. Anode is where oxidation happens, that is loss of electrons. Uh, so if you apply a voltage between the two, electrons will flow from the cathode to the anode, and that will complete the circuit basically. Okay. Okay, so this was the first step, the hollow cathode lamp. Now, before going to the previous step, uh, I'll just tell that, okay, I'll directly go to the next step. Okay, let's not go too deep into this. Let's see what happens next. Okay, so the next component in AS is what is known as entrance length, entrance slit, and collimating lens. Let me write it in terms of words. So the light from the lamp passes through a slit to make the beam narrow and defined. And what does this collimating lens do? It basically straightens the light. Collimate basically means straighten. See, it is true that I already told you in the previous class that when there is a slit and you pass electromagnetic radiation through it, there will be some minor diffraction. Okay. So here also there will be some minor diffraction. But basically this slit is not used for dispersion. Okay. That is done separately inside what is known as a grating. So, okay. So this is separate from that. So basically what we are getting from here is that the hollow cathode lamp will emit light, and this particular part, the second component, uh, will give us a narrow and parallel beam. Okay. And after that, we will go to the next steps. Curve slits. Okay. So there is something called a monochromator, okay, in an instrument which contains slits. They allow only a very narrow band of wavelength to pass through. So the narrower the slit, higher the resolution, but less the light. Wider slit means more light but lesser resolution. So our goal is to match the slits width to the element's absorption lines width. Okay. So third part, our narrow band of wavelength to pass through. Okay. So narrower the slit, less the light but higher resolution. So if I make a comparison between narrow slit and wide slit, this has less light will pass through, wide slit, more light will pass through. But here, less light, but better resolution. Then it is worse resolution. Fine. So our target is basically whatever the absorption line, okay, of our element that we want to analyze. That bit we have to match. Fluid wavelength, okay. So again, slit can be like fixed slit or variable slit or adjustable slit. As the name implies, fixed slit means the width is constant. Variable slit means the width can be adjusted. Okay, and adjustable entrance. They are used more in high tech instruments. Okay, and yeah, I think bandwidth and all So yeah, why we use slit is that because that particular sample may have many elements, right? So we want to measure only the trace amounts of one element at a time, not multiple elements. For multiple elements, we'll be using some other techniques. Okay. For instance, we can do that in ICP-MS, but over here only one element at a time. So if you want to tune into a radio, right, every radio has got a frequency, every radio channel. So if you want one station, you have to go to 98.4 or 102.5. Okay. Uh, if you're not very precise, okay, you can have noise from nearby frequencies, and that can spoil your experience of listening. Okay. So next step is step number 4. This monochromata can be prism or grating. So basically, this step is that uh, we have to isolate the exact frequency we want using slits. Okay, we controlled in layman's term. If I want to put, I can tell that the wave's purity we control, but we have to isolate the exact wavelength. Now, that this makes sense. So for that, this next step. Okay, prism uses dispersion, like different wavelengths bend differently, right? Depending on the refractive index. We saw that Newton's prism experiment from there. So likewise, grating uses diffraction. There is a formula also for diffraction, and I'm not getting into that. If we can always cover that if we have some examples based on this coming in your assignments or quizzes. So I did not see any. So you can either use prism or grating. Okay, that's why I put prism or grating over here. What is absorption? What is uh, dispersion? What is diffraction? Everything we covered in the previous classes. So prism uses dispersion. So when it is dispersion, think of the prism example. Grating, what does it use? It uses diffraction. So generally modern instruments use gratings, okay, because it has better resolution. Whereas prism is a little bit more old-fashioned. It was used in the earlier versions of the equipment. Modern instruments, for better resolution, they use grating. So again, like when you come to diffraction rate, there is something called coherence, incoherence, scattered light, all that. But If you want, you can study that on your own. But I'm not giving. I'm just giving you an overview here. So actually, I can always put this here only, but I'm still separating it. It's called exit slit because the equipment has something called this. So chosen wavelength. We have isolated the light that we want. Okay. So that chosen wavelength, it passes through the exit slit. It's a second slit, which fine tunes the band of light. Okay. So now that we have got the light that we want, let us send it through the sample where absorption can occur. So the next step is what is known as atomizer. Can be a flame or graphite furnace. So the sample is first converted to whatever sample that we want to analyze. Okay, say instance we have taken some groundwater which contains arsenic, say. Okay, so first we have to convert it into tiny droplets or mist. Okay, so that is what is technical term for that is it is nebulized. The sample is first nebulized. Okay, so I'll just write it down. What happens in atomizer? So nebulized is a technical term. What it basically means is it's converted into a fine mist of tiny droplets. So basically, what happens is that in a flame, there are two modes. Okay, one is called as a flame mode, one is known as furnace mode. In flame system, the droplets are carried by fuel and oxygen gases into a flame, where the solvent evaporates and the salt dissociates to produce free atoms. In the furnace mode, the sample is dried, then heated to remove water, and finally vaporized to generate free atoms. So these are two modes that we have. And the free atoms that are now released, they are the gaseous phase now. Okay, so they interact with incoming light, and some obviously some of that light will be absorbed. From there, we can make out how much of that particular trace metal is there. So I'll write it in terms of words. All AS instruments are just flame mode and furnace mode. Generally, flame mode is done for uh, a bit higher concentration, parts per million range, and furnace mode is done for parts per billion range. Okay, so this is what happens in flame mode. Droplets are carried by fuel and oxygen gases into a flame where the solvent evaporates and the salt dissociates to produce free atoms. In furnace mode, sample is tried. It's a graphite furnace basically. Sample is tried, then heated to remove water. Finally, vaporized, produce free atoms. Fine. So these free atoms right now that are produced by either of these modes, they are in the gaseous state. They can interact with light. Okay. So that light that has come through all those different stages, stages 1 to 5, they finally meet these free atoms, and some of the light will pass through, some of it will be absorbed, and basically based on what absorption happens, we will get to know what is the atom of interest. So next, so basically what happens, this is not a component, then just I'll break 6 into 2 points. I mean that with this particular whatever happens in atomizer into 2 points. Basically absorption happens. So selected light passes through the atom cloud. If the atoms of interest are present, okay, example zinc or lead, they absorb the specific wavelength, and this reduces the intensity of light reaching the detector. And the detector senses whatever the remaining light that has come, and that gives us an idea of the concentration of the trace matter. Say arsenic. They absorb the specific wavelength that is of arsenic. This reduces the intensity of light, and remaining light passes to the detector. Hmm. So by now it must be obvious to you what is our next step. Our next step is the detector. Okay, so here there is one more concept that is known as photoelectric effect. This is what fetched Einstein the Nobel Prize. So this is a concept that we'll use in detectors. So so what is a photoelectric effect? Basically says that we know that light has got a dual nature, no? It can be a wave as well as particle. So the particle is what is known as photons. Right, particle. So when these photons hit a photosensitive material, that material ejects electrons. That number of ejected electrons is proportional to intensity of incoming light. Okay, so thus you can convert it into current because electrons, if they are going to be, there is motion of electrons going to be involved, there will also be some particular current, and that current is read as signal. Okay, so though like I don't think these things will come in the exam, but the photoelectric equation basically goes as the electrons that is ejected by the material, right? So the kinetic energy of the emitted electron, which goes as h into frequency minus w, where h is with Planck's constant. This is the obviously the frequency, and w is what is known as a work function. So what is this kinetic energy? Kinetic energy of emitted electron, and this is work function. Okay, h of course you know it is Planck's constant 6.62 into 10 to the power minus 34 joule second. This work function is material specific. So obviously, like if h nu is less than the work function, there will be no emission. Okay, so work function is basically the minimum energy needed to eject electrons. W, that is work function. Minimum energy to eject electrons. If energy is less than W, the electrons will vibrate, but there won't be any emission. No electron emission means no current, no signal. Okay, so this is one thing I wanted to get out of the way. So because sir discusses photoelectric effect now, it was in context of this detector only. Okay, and yeah, just remember, keep in mind that work function varies between metals. So basically, from this we see that light is converted to measurable signal. Okay, so basically the light hits a photoelectric detector, a photosensitive detector. Electrons are emitted because of which there is electric current, and you can measure the electric current. So that's a signal for us. So it correlates the light intensity to the electric current. Okay, and more the absorption. That means uh, the trace metal that we want to detect, that is more in amount. Okay, so it detects most of the light, and then the light that is striking the detector will be less, and the signal will also be weak. But if it is less, the trace metal is very less. That means it allows most of the light to pass through, and there'll be more current. So like that, they make the calculations in the machine. So that's the journey of the light from the lamp to the detector. Okay, so yeah, basically the emitted electrons, right? They have some kinetic energy, and there is some they strike an electrode. Okay, there is a photomultiplier tube. I'm not getting into all of that, but there is a process by which the kinetic energy of the electrons becomes current in the detector. Okay, you just need to know that. Okay, so coming to the prism, okay, because a couple of questions in the assignment I saw related to prism. So this you check as homework, okay. I'm not getting into the technicalities, but there are a couple of things that you want to see. One is known as a Cornu prism, and one is known as a lit Grau prism. I mean, I can do these things, but I feel like uh, it's just time consuming, okay? Because anyway, prisms are not used in the modern equipment. Okay, modern equipment is more diffraction based. Since one of the questions asked in the assignment was related to prism, that's why I'm giving it to you as homework. So, instance, like there is a question in the previous year assignment which we will solve at the end of the class, hopefully, about lead ground configuration. In lead ground configuration, the incoming and outgoing light beams travel in the same path but in opposite directions. Okay, so like if you throw a ball at the wall and the ball bounces back to you now, so it strikes the wall and comes back, the path is same to opposite direction. So it's something like that. Okay, uh, like that there is something called cornu prism also. But these things, like why we don't uh, why I won't be covering it is that because in modern instruments they are replacement diffraction gratings. Modern instruments. Okay. So maybe take a small 5 minutes break. 37 minutes is already up. Yeah, take a small 5 minutes break and then we will assemble and go to the next part. Okay. So I'm trying to cover everything that Sir also covered in the class. So he covered this types of energy levels. So basically, in atoms and molecules, they interact with electromagnetic radiation by transitioning between discrete energy states, okay, or the quantized energy states. And these states differ depending on whether it is an atom or molecule. For instance, for an atom, basically an atom is an elemental form, right? It possesses only electronic energy. Yeah, possess spelling. See, yeah, electronic energy levels only. So what is electronic energy level? It's a fixed amount of energy that an electron can have as it is orbiting the nucleus. Okay, they can't have any energy, right? They can have only certain energy levels depending on what shell or orbital they are uh, orbiting in. Like we saw now KLM and these kinds of shells that is n is equal to 1, 2, 3. So each has got a particular energy level, and each level corresponds to a specific distance from the nucleus and has a specific energy value. So we saw all this in the first class itself, so I'm not repeating myself. I just want to make a couple of additional points. I write it in words first. Okay, so if an electron absorbs energy, example from light or heat, it can jump to a higher energy level. That is what is known as excitation. And if it later releases energy, it falls back to a lower level. When that happens, it emits light in the process. Again, that steps in ladder analogy. I'm not repeating on that, okay? So let's come to molecules now. So in case of molecules, in addition to electronic levels, because it molecules also comprised of atoms now, so it will obviously have some electronic energy level also. So in addition to electronic levels, these molecules exhibit two other types of energies. One is known as a vibrational energy level. This is due to oscillation of bonds which connect the two atoms. Because of their oscillation, there is something called a vibrational energy level, and another is rotational energy level due to rotation around the axis. Fine. So I'll just read some text. I won't write this down. So these form a fine structure within the broader electronic levels. That is this vibration and rotational energy levels. They form a fine structure within the broader electronic levels. Basically, if you think of each electronic level like a shelf, okay, you have these shelves at home, right? So in each shelf, there are smaller compartments. So these are our vibration levels. And in these compartments, if you make further divisions, those are the rotational levels. So the energy isn't just one big jump from one level to another level. There is a detailed substructure. So often in books, they tell that these form a fine structure within the broader electronic levels. So in molecules, vibration and rotation levels act like finer subdivisions layered inside each electronic level, creating a detailed structure of possible transitions. And the energy hierarchy will go like this: electronic energy is much larger than vibrational energy, is much larger than rotational energy. Okay. So imagine person jumping across stones in a river. Okay, in a river there are many stones, and that person is jumping across the various stones. So jumping between two stones far apart, like it will demand more energy from you. That is the electronic transition. And hopping between two closer stones, that is vibrational transition. And when you land, okay, when you have a twisting motion in your body, that is a rotational transition. So each of them is layered with an electronic transition. Each motion needs different energy, just like from large energy to small energy. Couple of other concepts I want to cover here. Ground stated, ground state versus excited state. Ground state versus excited state. So ground state is at room temperature. Okay, ground state is the lowest possible energy configuration. It default is at room temperature. While excited state is when the system absorbs energy and jumps to a higher state. Higher state meaning electronic or vibrational or rotational. Okay, sometimes there may be even be partial excitations, uh, where the atom or molecule may absorb only a small amount of energy, not enough to reach the next electronic level, but enough to shift within the sublayers, that is the vibrational or rotational sublevels. So these are what are known as partial excitations. So there is something called partial excitation also. Just keep that in mind. Okay, so I will talk a little bit about the historical development of atomic absorption. Though in this case, I may not go into very too much details because these things are generally not asked in the exam. But I can give you the names of the scientists involved, and you can further Google them. I will just I will just mention what is their importance in the development of atomic absorption. I will mention the names of the scientists so that you can Google on your own if you are interested. So the first person is William Wollaston in 1802. So I will just read what they have done, and yeah, but I won't make all the notes and all because like it will be too irrelevant, I feel. So Wollaston was experimenting with sunlight passing through a prism when he noticed several thin dark layers interrupting the continuous rainbow-like spectrum. These dark caps were unlike anything observed before. He couldn't explain them at that time, but this is the first recorded observation of what would later be known as absorption lines. Okay, so if you remember Newton's prism experiment, where if you pass white light through it, okay, you pass white light through it, it splits into different colors. That is Vibgyor, because each of them has got a different refractive index. So when it pass meets a glass prism, the material is glass. Each of the wavelengths slows down to a different extent, and because of which some light bends more, some light bends less. Like blue bends more than red, etc., etc. And you get this prism of colors. That's a rainbow color, right? Vibgyor. What Wollaston, while doing this experiment, okay, he noticed that there were several dark lines, okay, interrupting the continuous rainbow-like spectrum. These weren't observed before, okay, and he couldn't explain them also. But this was a very important observation that he saw. And the next, just come to the next scientist in 1814. There's a guy called Joseph Fraunhofer, a German scientist, a German optician to be more precise. He improved upon Wollaston's observation using better instruments like telescopes and high quality prisms. He mapped over 500 dark lines in the solar spectrum. These were later named Fraunhofer lines in his honor. He also noticed that some of these lines matched the light absorbed or emitted by known elements. Okay, so in solar spectrum, he found 500 dark lines and he named them Fraunhofer lines. I mean, he did not name them; they were later named in his honor. And what he noticed is that some of these lines match the light absorbed or emitted by known elements. I told now every element has got a particular energy level at which it absorbs or emits. So, corresponding to that, he found these dark lights. And around that period only, early 1800s, there is a famous English scientist. His name is Sir David Brewster. He suggested that the dark lines were due to vapors of elements like sodium and iron in the sun's outer layer, absorbing specific wavelengths of light. This was a major shift in understanding that the sun's atmosphere could filter out certain colors. So, what this Sir David Brewster said is that there are in the sun's outer layers, okay, because sun is only emitting our light. In the outer layers of the sun, there were some vapors of elements like sodium and iron, and these were absorbing specific wavelengths of light, because of which we were seeing all these dark lines. Okay, so he gave an explanation why this was happening. First possible explanation. Then in 1859, person named as Gustav Kirchhoff, the another person, Robert Bunsen, is also credited for this, but Kirchhoff more. So, but together, both of them, they made a very important breakthrough in spectroscopy. They discovered that when you heat an element, example sodium, it emits light at very specific wavelengths, creating sharp emission lines. More importantly, they found that if a light containing these wavelengths is passed through a cooler vapor of the same element, the same wavelengths get absorbed, creating dark lines in the spectrum. This is what is now called as Kirchhoff's law of radiation. So, what is Kirchhoff's law of radiation? So, you understand, right? So, they are basically saying that when you heat an element, okay, example sodium, it emits light at very specific wavelengths, and that creates sharp emission lines. They found that if a light containing these wavelengths is passed through a cooler vapor of the same element, that is sodium, the same wavelengths get absorbed, creating dark lines in the spectrum. So I'll just list Kirchhoff's law of radiation here. Basically, wavelength will always represent as lambda. Okay. Kirchhoff's law of radiation is that an element or compound absorbs the same wavelength of light that it emits when heated. Okay, so this gives us an explanation for Fraunhofer's observation. Brewster suggested that there's something like this is happening, and Kirchhoff, through his law, he basically confirmed the theory behind why these dark lines were occurring. So this principle explained the dark lines in the solar spectrum and allowed scientists to identify what elements were present in distant stars simply by analyzing their light. Okay, so mainly astrophysicists they employ this method. There are many distant stars, right? Like millions of light years away. The light that they emit, they analyze those light patterns, and they can identify what elements are present in those stars, which are millions of light years away. In 1860s, there was a French guy. His name was Foucault. So he did not propose any new theory, but he performed a very clear and visual confirmation of Kirchhoff's earlier findings. He designed a simple experiment where bright sodium light was passed through cool sodium vapor. He observed that the bright emission lines became a dark absorption line, a phenomenon known as spectral line reversal. Okay, so through his experiment, he confirmed basically what Kirchhoff said. The technique is known as spectral line reversal. So if you want more details about this, I can share the notes and all. I don't think it is required for your exams, but feel free to ask in the forum. Like if you want more clarification about these things, I can. I'm not writing everything down. Okay. So see, Kirchhoff and Bunsen they explained the principle, but importance of Foucault's contribution was that he visually demonstrated the idea through experiments. So the scientific community at large could see it with their own eyes in action, and that further led credence to Kirchhoff's law. In 1902, there is a guy called Robert Wood from America. So he's our next big name in this particular technique. His name is Robert Wood. Okay. So Wood passed sodium light through sodium vapor and observed reduced intensity. He extended this idea to detect trace mercury using acoustic resonance. Though still a physicist's tool, it hinted at potential for trace metal analysis, which is a major use of AS today. Okay, and in between 1920s and 1930s, scientists had data on atomic spectra, but again they saw AS as a phenomena, not as a technique, experimental technique to analyze trace metals. So instrument development, the foundations of which were laid post 1924. Okay, this is when we see a real shift in action. Like there are some scientists whose names are Angerer, Choose, Frame, Smita. So they created tables of absorption lines for elements like aluminum and indium, and their efforts transformed AS from a curiosity phenomenon into a technique for experimental analysis, and this led to instrument development to the mid 20th century. Okay, so basically, like when I was telling about the first observation, right? William Wollaston's that he passed light through prism and he saw dark lines. So the first experiment like this was done by Newton. Okay, Newton like he was very versatile person. He worked on a lot of things, and optics was one of the areas. So he also used a prism to split white light into its seven colors. Okay, but he did the experiment in the 17th century, mid mid 1600s or something. Okay, and he did not report any dark lines. So your curiosity may ask you like why Newton did not observe all this, because at that time in the 1600s his experimental setup had very low resolution because he used basic glass lens and wall projections. Okay, he did not have any telescope or any slits or sensitive detectors. Those came much later in the 19th century only. So his main focus was to prove that white light contains many colors and not on finding any intensity dips. Okay, but by the time Fraunhofer and others came in, uh, they had access to better instruments. Okay, so they had access to things like high resolution prisms, diffraction gratings, because of which they could observe the dips in intensity at specific wavelengths. So yeah, basically Fraunhofer lines or dark thin lines observed in the visible spectrum of sunlight when passed through a high resolution prism or diffracting grating. Fraunhofer mapped and labeled these lines systematically using letters. Example D line for sodium, H and K for calcium, etc. Each line corresponds to a specific wavelength absorbed by an element in the cooler outer layers of the sun's atmosphere. These lines are essentially the solar spectrum's fingerprints or elements like calcium, hydrogen, sodium, iron, magnesium, oxygen, water vapor, etc. So there are some Fraunhofer line wavelengths. I'm not going to list them down, but at particular wavelengths, the it corresponds to some elements. Okay, like 4,500 angstrom for iron, 5170 angstrom for magnesium, 5890 for sodium, like that. Okay, so you may ask why are Fraunhofer lines relevant for an AS course? And why did Mudakabi sir like spend one class on all this? Because Fraunhofer's lines, they were the first real world evidence of atomic absorption. Okay, they showed that atoms in the sun's outer layers absorb specific wavelengths of light, and that same principle we are going to use in AS also. So what nature revealed through sunlight, we will now recreate and measure in laboratories using modern instruments. So I'll just do a comparison between Fraunhofer and AS. So in nature, they are observed Fraunhofer lines. Nature meaning in sunlight. So I'll just write the analogy between these two. So in case of Fraunhofer lines, sunlight passes through elemental vapors, and in case of AS, lamplight passes through free atoms in a flame or furnace. So in case of Fraunhofer lines, some wavelengths get absorbed, resulting in dark lines. Here also some wavelengths get absorbed, resulting in reduced intensity. Okay, so Fraunhofer line helps. It's mostly in the astrophysics area. It helps in identifying elements in stars. AS helps in identifying elements in samples. See, another thing way to look at is that sun is also like Earth is also like a byproduct of the sun only, right? So most of the elements that are found in Earth are also found in the sun. So Fraunhofer lens are essentially astronomical spectroscopy in celestial bodies. Okay, so yeah, basically AS is like a very powerful analytical tool used for detection and quantification of metals, especially at trace and ultra trace levels. Yeah, as I already explained, AS basically measures the amount of light absorbed by the free atoms in the gaseous state, because each element absorbs light at specific wavelength, and the amount of light absorbed is directly proportional to the concentration of the element in the sample, based on the Beer-Lambert's law, which I mentioned in the first class. So just refer to that. Okay, so by now you must be familiar why we are learning AS and all. What are the applications of AS? Why we should care about it, etc. Okay, so we went through the electronic transitions, vibrational mode, rotational mode, Kirchhoff's law, Fraunhofer line, the evolution of how AS came into being. And just before taking another break, I will just add a couple of more important contribution by scientists. So there are a couple of other scientists you can Google about them. Okay, Mueller and Kringshin. So they were basically 1890s to 1900s. Those 2 decades. They were the first people to study spectral line absorption and emission in laboratory settings. Okay, and their experiments helped demonstrate that atoms absorb the same wavelength they emit, supporting the reversibility of spectral lines. Later confirmed by Foucault, or earlier confirmed by Foucault. Foucault was 1816, and they were after Foucault only. So basically, their work laid for the groundwork for understanding line spectra. In laboratory settings, they studied all the spectral line absorption and emission. So these are some other important names. And there is another person a bit late, okay, Alan Walsh in 1955. Alan, A-N-A-L. He was an Australian guy, Australian physicist, okay. His importance is that he proposed the use of AS to detect metals at ultra trace levels for the first time. Before him, emission methods, okay. I told you the emission, when an atom is excited, it goes to higher energy level, and when it comes back to lower energy level, it emits light. So those kind of experiments were more dominant. But Walsh recognized that absorption could offer higher selectivity and simpler spectra. His approach enabled scientists to directly measure ground state atom absorption using line sources such as hollow cathode lamps. So Walsh's proposal laid the foundation for commercial AS instruments that began appearing in the 1960s, and by 1970s it just blew over. So like you can call him the father of AS, okay? Because he was the guy because responsible for using AS to detect metals at ultra trace levels. And he told that absorption methods are better than emission methods. So that's his importance. So it's another big name. So yeah, maybe we'll take a 5 minutes break, and after that we'll look at the next part. Okay. Okay, so it's already almost 1.5 hours in today's class. I have to wrap it up quickly, so let's quickly go to the next part. Evolution of instrumentation. Okay. So first is, I think these things will again discuss in the coming classes. Photo multiplier tube or PMT. So this is a highly sensitive detector used in AS to measure light intensity. It works like a light amplifier. So I already told you that when photon hits detector, it releases an electron, and this electron creates a strong electrical signal. But to detect the signal, even for from when the source is a weak light, you use this photomultiplier tube, okay, which multiplies the electrons through a series of some other plates called diodes, and because of which you can detect very low light level also. So it's like a microphone, okay, which can even pick up the faintest whispers of light. So that is what is a photomultiplier tube. Like that, there is something I want. You can just refer it on your own homework. I'm just giving out the all the names of the instrumentation which are used to better the readings. Okay. Another thing is called beam modulation. Then there is something called chopper wheel. So just read about this. Okay. Can you say the Chat GPT or Wikipedia anything? Uh, like what were the problems in the earlier AS instruments and how these instrumentation techniques, the instrumentation that evolved over time, how they solved the earlier problems. Okay. So just read about it. Then also read about double beam modulation. Not sure whether these things will come in your exam or not. To have a better understanding of AS, you can always refer these things. So basically, all these techniques are used to improve the signal detection. Okay. Uh, it further evolved. Okay. Like I already told you about flame AS and furnace AS. Okay. I already told you about flame and furnace, flame mode and furnace mode, how they. So furnace is even more advanced than flame. It can measure at ppb level, whereas this can measure only at ppm level. So like that, there is something called hydride generation, AAS. So it converts the metalloids like arsenic, selenium into volatile hydrides for easier detection. This works in combination with a flame or quartz tube atomizer. Okay, so quartz tube atomizer is a small transparent tube made of quartz placed in the furnace. The hydrate gas enters the heated tube where it breaks down thermally, releasing free atoms. These atoms absorb the light of the lamp just like a normal AS. So why we use quartz is that it allows high temperature operation and transparency to UV visible light. Okay, so I just write what it is. Hydride generation AS. You can just read about that. And in conjunction with this also read about the quartz tube atomizer. So these are all the developments that have happened in this area, especially in terms of instrumentation. So like that, there is something called CVAS, which is cold vapor as AS. So cold vapor AS is designed specifically for detecting mercury at ultra trace levels. Okay, because it's based on the fact that elemental mercury is volatile at room temperature, so it's directly carried into the optical path without the need of any flame or a furnace, and it allows for extremely low detection limits. See, mercury detection is a bit different from other elements. That's what they found more challenging. So that's why the CVAS technique was developed. Cold vapor generation of mercury. Okay, so researchers like Stock, Henschel, Harch, Watt in the 1960s and 70s, they laid the groundwork for mercury monitoring also. See, especially countries like Japan and South Korea, etc. In that area, there's a lot of mercury poisoning in the ocean. And when they eat the fish, they also get that. It enters the food chain also via fish. There's something called Minamata disease. You must have heard. It's a neurological problem. It happens in Japan. So that's again because of ingestion of mercury. So mercury detection was quite important for that. Okay. So the one thing I forgot to mention is that I told you about ground state, excited state, etc. But when it comes to electronic transitions, not all transitions are equally strong. The most intense one is also known as resonance time. So here the transition is from ground state to first allowed excited state. So when transition is from ground state to first allowed excited state, that's the most intense transition, strongest transition. It's called resonance line. So another thing I want to tell about is the Gaussian diagram. Because sir covered these concepts, that's why I'm refreshing them. So basically, it's like tells us what kind of transitions are allowed. It's a roadmap of the atom's energy levels. Uh, these diagrams help scientists identify which energy levels an atom can jump between by absorbing a particular wavelength of light. Okay, so in simple terms, that is what it is. Uh, Gaussian diagram. I think you can refer to Sir's notes. Like yes, I don't have the note presently. Sorry for that. Uh, yeah, but basically, what a Gaussian line diagram is used for is that it tells what all transitions are allowed. Okay. So there is something called Bohr's equation. These things I'm just mentioning because Sir has covered it in class. In case some exam in exam something comes. So basically, from this equation only it has come, and lambda is 1.23978 by delta E in electron volts. This is the Bohr equation, okay? So it so basically here it connects the energy absorbed by an electron to the wavelength of light. So Bohr postulated that electrons move in specific orbits or energy levels without radiating energy. And when an electron jumps from lower orbit to a higher orbit, it absorbs a photon, that is some light. And this energy difference, use a formula like En is equal to minus 13.6 pi n square in terms of electron volt. And delta E is therefore from one from when it goes from one orbit to another orbit, delta E is like minus 13.6 into 1 by n2 square minus 1 by n1 square in electron volt. And once delta E is known, using this equation and E is equal to hc by lambda, from there you can find this particular. I'm not. I mean, that's how it's derived basically. So it helps predict what color of light will be absorbed. Okay, whatever delta E is there, based on that we'll get some wavelength, and then it will help us predict what color of wavelength will be absorbed. So basically, it connects the energy difference between two levels to the light's wavelength, and it helps in choosing the right cathode lamp. Okay, for example, if delta is equal to say 2 electron volt, then just by this uh, lambda you will get around 620 nanometer, which is red light. So that helps us to choose the cathode lamp. So use of Morse equation I just write here. I'm not getting into the derivation part and all. Helps predict what color. Again, color is a function of wavelength. So it's used to calculate the exact wavelength an atom will absorb, and thereby helps in choosing the correct cathode lamp, hollow cathode lamp for analysis. So I already told you what ground state is, what excited state is, right? Ground state is the lowest energy level of an atom. Its most stable condition. But when it absorbs energy, it electron goes from a lower level to a higher level. And this is the excited state. And excited states are unstable. So when the atom comes back to lower level, it emits energy. Okay. So that's atomic emission. In atomic emission, atoms in the excited state return to the ground state by releasing energy in the form of light. So that is the basis of firecrackers. Okay. In firecrackers also the same thing happens. Uh, upon de-excitation, the atoms emit light, and the emitted current depends on the element and its transition wavelength. For instance, sodium means bright yellow, potassium is violet, calcium is brick red, strontium is crimson red, barium is apple green, copper is blue green. So in fireworks and all, you'll get all these the elements only are present in the firework, like strontium, calcium, barium, copper, and they give uh, rise to the various colors. So instruments that use atomic emission, they can be like ICP OES or flame emission spectrometer. Okay, they're also used for multi-element analysis, but here the technique is emission. But we are interested in absorption, atomic absorption, where atoms in the ground state absorb light to jump to higher energy level. Okay, so absorption starts at the ground state, emission starts at an excited state. And at room temperature, generally the thermal energy is not sufficient to excite atoms. So atoms generally stay in the ground state. Uh, Instruments that use atomic absorption include AS, and AS can again be flame AS or graphite AS, graphite furnace AS, hydrogen generation AS, cooled vapor AS. All these things we already saw, okay? And creating free atoms. Why solids don't work is that atoms bound in solids cannot absorb radiation because they are part of the lattice. So you must free the atoms from the solids by thermal energy, say by a flame or a furnace or hydrate or cold water vapor generation. Mercury is already a vapor at room temperature, but most of the other elements only at heating they release the vapor form. Okay. So I just make a note of it that already ground state, excited state, I already explained to you. Emission, just think of fireworks, okay? As an example. Sodium, bright yellow, potassium, violet, calcium, brick red, strontium, barium, green apple, that's the color. Copper is blue. Okay, so basically in emission, when the atoms emit light upon de-excitation. Okay, whereas the real world application can be a flame emission spectrometer or ICP-OES or ICP-AES, atomic absorption emission spectroscopy. Okay, but we are interested in absorption. Case of AS, atoms in the ground state absorb light to jump to higher energy levels. Okay, so that's the difference between these two. And I already told you that AS measures the reduction in light intensity due to absorption by ground state atoms in a vapor. So the key difference between absorption starts at ground state, emission starts at excited state. And I already explained why solids don't work because they cannot absorb radiation. Free atoms are required to absorb radiation. Okay, so there is this also we mentioned that not all transitions between energy levels are allowed. There are some quantum selection rules which determine whether a transition can happen or not when atom absorbs or emits light. Okay, okay, so there are some other things like electric dipole transition, change in angular momentum, opposite polarity, etc. I'm not getting into all the details because I don't think we can even this post. Just make sure that there are some rules which explain why we see some absorption lines and why we sometimes don't see absorption lines. Okay, only specific wavelengths are allowed, and some transitions are forbidden. That is why AS is element specific because each element has its own set of allowed transitions, leading to identifiable sharp spectral lines. And I also already told you about the resonance line. Okay, so it's the most intense line. It arises from the transition between ground state and first excited state. So, Sir told you about Einstein coefficient, some formula he gave it. Basically, in atomic spectroscopy, not all electronic transitions are equally likely. Some happen frequently and produce strong lines, while others are rare or forbidden. So this likelihood is determined by Einstein coefficient and oscillator strength. So these equations help us like predict how many atoms in a population will absorb photon at a specific wavelength, how quickly excited atoms will return to lower energy levels, the intensity and sharpness of spectral lines observed in electrons. Like he must have given an example of spontaneous emission rate. That when an atom in an excited state returns to dual energy on its own, it emits a photon. The rate at which it happens is given by, so it goes from 1 to 2, A into N1 into dt, where A is the Einstein coefficient for spontaneous emission, right? I mean, all this and all, I don't think they will come in the exam. I'm not going into details of all these things, but if some assignment problems comes in this area, just let me know. I will go in more detail. Okay, almost 2 hours is up. I have to go to the problems also now. So like that for absorption also, like this probability of spontaneous emission rate, like that for probability of absorption. Absorption also there is one more thing. Again, some Einstein absorption coefficient is there. Volume flux density at a particular frequency is there. Then oscillator strength, right? Uh, which quantifies the strength of the absorption or emission transition. So that's some equation called pi e square lambda into f divided by mhc. So all that, like, we'll see whether if they come in the exam, I'll go into details and maybe even solve an example, but I don't think we need to try. Okay, so I'm not going into details of transition probability and Einstein coefficient over here. Basically, just to mathematically quantify the absorption or emission. Okay. Yeah, I think that's it. I already told you there is something called absorption. There is an equivalent equation for absorption, right? Something called oscillator strength also. So maybe just start going through these examples. Okay. I'll upload a problem sheet too. Okay. So just go through that once. Maybe take 5 or 10 minutes to solve them, and I think there's some 8 problems, right? 10 problems. Okay. Very simple problems only. Just go through them once, and I uploaded it. Since none of you is in class, you do it at your own leisurely time, and then I'll just tell the answer just after maybe 5 10 minutes. Okay. Okay, let's look at this. Magnetic quantum numbers varies from minus L to L, right? Like if it is 2, L is equal to 2, then azimuthal quantum number, the magnetic quantum number can be minus 2, minus 1, 0, 1, 2. So 5. Like that it will be. A plane polarized electromagnetic wave has vibration in one plane, all directions between two poles. So has vibration in one plane. Energy of photons in an electromagnetic radiation is independent of intensity of light, proportional, inversely proportional. What? So here it's independent of intensity of light. Intensity of light is nothing now. Think to do with energy. It depends on the solid angle, right? Like if the solid angle is very small, intensity is more. That's why like torch, if you flash a torch from far away towards the wall, intensity won't be much. But as you come closer to the wall, the solid angle reduces and you'll have more intense light. In normal dispersion for a given media, there are four options. What happens to refractive index with frequency? Okay, so problem sheet 2, ES2. So the correct answer over here is that refractive index increases with increasing frequency. I'll tell you why. See, what is dispersion? Dispersion is that when light of different colors bends when passing through a different material. So, for instance, we saw the prism experiment, right? When light fell on a prism, it split into many different wavelengths, right? So, violet here, indigo, blue, and topmost was red. So, blue bent more compared to red. So, blue has got higher frequency. Blue, violet have got higher frequency, and it bends more means that slower speed. Red is frequency lower and higher speed. In that particular medium, for red color, the speed is higher. That's why it bends less. And what is refractive index? Refractive index is just speed of light in vacuum by speed of light in the medium. And if blue and light have got slower speed, that means C by N, C by V, that is N. The refractive index will be higher, and here the refractive index will be lower, right? Because like blue light bends more than red light because it slows down more in that medium, and we know that blue light has got higher frequency. So since it slows down more, therefore C by V, where V is the speed of light in that medium, light is slower. So C by C is constant, C to 10 to the power 8 meters per second. So it will be higher in this case for blue light than for red. So the correct answer is that refractive index increases with increasing frequency. What is the next question? Next question is Pauli's exclusion principle states what? Yeah, no two electrons can have the same set of quantum numbers. Option 3. You refer to the first class notes, okay? Problem 6. Literal mounting. In literal mounting, the correct answer is I asked you to do self study in this case, but the correct answer is dispersed radiation is collected on the same side. Okay. So you do self study in your own case, but I mentioned in passing that the input and output beams lie on the same side in case of literal mounting when we were discussing prisms. Okay, I did not expand much into that because modern AS instruments use uh, slits gratings rather than prisms. But still, I mentioned that the input and output beams lie on the same side, follow the same path, albeit in different direction. So this is the option that matches it the most. But anyway, you can do self-study, okay? You can even see like how that prism looks like. Seventh is what is the value of Planck's constant? It's obviously 6.6254 into 10 to the power minus 34 joule second. The energy of 413 nm nanometer photon, the visible radiation is how much? So the wavelength is given, right? So just apply the Planck-Einstein equation, okay? For the eighth problem, just apply this equation. E is equal to h into c by lambda. You know h, it is 6.626 into 10 to the power minus 34 in SI unit, of course. C is 3 to 10 to the power 8. Of this lambda, lambda is 430 nanometer or 430 to 10 to the power minus 9 meter. So when you make the calculation, we get approximately, sorry, your energy will approximately get as 4.62 into 10 to the power minus 19 joule. And the option which matches it the most is 4.62 into 10 to the power minus 19. Okay, so wave number. What is wave number? Wave number is just 1 by lambda. Like lambda unit is centimeter, so wave number will be centimeter inverse. Say I represent wave number as, say, like this. If I represent what is E, h into frequency, or h into c by lambda is equal to hc into nu bar. Therefore, from here we can see that energy is directly proportional to wave number. That means wave number increases with energy of photons. Dark lines in solar spectrum are due to absorption by atomic vapor of some elements. Okay, so this also we saw the Fraunhofer lines, the dark lines, the solar spectrum, that are the Fraunhofer lines. I also told you now that the hot core of sun emits within a spectrum of light, but as this light passes through the cooler outer layers, certain wavelengths are absorbed by the atoms present. Example, sodium. So because of which you get these dark lines. So it's just that Fraunhofer lines. So the answer is absorption by atomic vapors. So scattering is different. Scattering is like in evening, like the sky of the sun that you see, that is because of scattering. Uh, Non-emission of certain wavelengths doesn't make sense because sun emits all wavelengths, right? Some lines disappear due to absorption, not due to lack of emission by the sun. So the correct answer is this two. Okay, I think that's enough for today. It's already almost 2 hours today. Let's stop the recording. Thank you. Feel free to hit me up with any doubts if you want in the forum. I'll end the class now. Thank you.